Thank you for being a friend. Travel down the road and back again. Your heart is true. You're a pal and a...
In this video, we want to talk about what's called the primary decomposition theorem, which is an equivalent form of the fundamental theorem for finitely generated abelian groups in the case that your abelian group is actually finite. In order to do that, I want to build on something that we talked about in the last video. So suppose we have G, a finite abelian group of type n1 up through ns. So G is isomorphic to z mod n1z cross z mod n2z up to z mod nsz, where each one of these nj's is at least 2, and ni plus 1 divides ni for all I. So we said last time that for each prime p dividing the order of G, p divides n1 at least as many times as p divides ni plus 1. Why is that true? Because otherwise it's not possible for ni plus 1 to divide ni. So I want to put some notation behind this. So let's say that m is a positive integer and p is a prime. We can write m as p to some power, p to the alpha, times r, where alpha is greater than or equal to 0, and p doesn't divide r. We've already seen this like when we were talking about finding the order of a Sylow p subgroup of a group. We're going to define VPM to be alpha. So what is VP? It's this p-adic valuation function. That sounds fancy, but it's just saying how many times does the prime p divide m? What is the highest power of p, the highest exponent of p, so that p to that exponent divides m? And now, for each prime p dividing the order of G, which is this product of n1 up through ns, which we'll call n, I claim that we get a partition lambda p, where I want to put the p at the top for a reason I'll explain in a second, of Vpn, the number of times that the prime p divides the order of this group. What is that partition? Well, the entries are going to be Vp n1. How many times does the prime p divide n1? And then Vp n2. How many times does the prime p divide n2? And then Vp n3 up to Vp nt, where t is going to be the last one of the invariant factors, nt, where p divides nt, but p doesn't divide the next one. So at some point, p is just going to stop dividing your invariant factors, and that's where you cut it off. Because what do we want out of a partition? We want each part in the partition to be greater than or equal to 1. So we don't want to include a bunch of things where p doesn't divide nj at all. So when did we talk about partitions before? When we talked about the cycle type of a permutation. So what does this mean that this is a partition? When we talked about cycle types, unfortunately, we insisted that the parts of a partition go in non-decreasing order. So they go from small numbers to large numbers. But here we're going the other way. We're going to say that the parts of a partition are going to be in non-increasing order. So VPN1 is going to be the biggest one. VPN2 is going to be can be equal, but it's not going to be bigger. We know that the order goes this way. The number of times p divides n1 is at least the number of times it divides n2, which is at least the number of times it divides n3, up through the number of times it divides nt, which is at least 1, and then p isn't going to divide any of the invariant factors that come later. So what is true? Well, the number of times that p divides n1 plus the number of times it divides n2 plus the number of times it divides nt, that's going to be the total number of times that p divides this direct product. That is the total number of times that p divides n, or the order of G. So what are we seeing? If you start with a bunch of invariant factors, then you get a partition which comes from the number of times p divides your first invariant factor, the number of times p divides your second invariant factor, and so on. So I'm going to pause and erase and explain how this leads to what's called the primary decomposition theorem. In order to explain how the material we've been developing leads to the primary decomposition theorem, we need one more fact, which is proposition 6 in section 5.2, but really is something that we've been talking about for a very long time. So it just says first that Z mod MZ cross Z mod NZ is isomorphic to the cyclic group Z mod N M N Z if and only if the GCD of M and N is 1. Second, if N factors as a product of prime powers, P1 to the alpha 1, P2 to the alpha 2, up to Pk to the alpha k, where P1 up through Pk are distinct primes, and each alpha I is greater than or equal to 1, then Z mod NZ is isomorphic to Z mod P1 to the alpha 1Z cross 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 Pk to the alpha k Z. And there are a bunch of ways to prove this. I mean, one thing that you could do that would be, I guess, sort of overkill, given what we've done so far, is, the second statement looks a lot like the statement that Z mod NZ is isomorphic to a direct product of its Sylow P subgroups. When you have an abelian group, each one of your subgroups is normal. So in particular, the Sylow P subgroups are normal, so they are unique. So I won't say anything more about that, but you can prove this much more directly as well. If the GCD of M and N is 1, then 1, 1 is an element of Z mod MZ cross Z mod NZ that has order M times N. So this group is cyclic. Here's an argument that's a little bit different than the one in Dummett and Foote. If the GCD of M and N is D, which is bigger than 1, then Z mod MZ cross Z mod NZ has a subgroup isomorphic to Z mod DZ cross Z mod DZ. So in particular, it has a subgroup that's not cyclic. How do you know it's not cyclic? Every element in here has order at most D. So the subgroup's not cyclic, which means Z mod MZ cross Z mod NZ is not cyclic. And then how do you prove the second one? Well, you can use it to prove this doing the first one plus induction on K. Okay, so why are we bringing this up now? What does the primary decomposition theorem say? Let's say that G is an abelian group of order n, and it's bigger than 1, so it's not the trivial group. So n can be written as a product of prime powers, P1 to the alpha 1, P2 to the alpha 2, up to Pk to the alpha k, where P1 up through Pk are distinct primes, and each alpha I is greater than or equal to 1. Well then first, G is isomorphic to a direct product of groups A1, A2 up through AK, where each AI is an abelian group of order Pi to the alpha I. So thinking about the orders, this matches up at least. The left-hand side has order n, the right-hand side has order P1 to the alpha 1 times P2 to the alpha 2 up to Pk to the alpha k, and that is n. And then each one of these groups, A1, A2 up through AK, can be written in a nice way as a direct product of cyclic finite abelian groups. So for each A in A1 up through AK, we'll just say that the size of A is equal to P to the alpha. So we're trying to get rid of the indices to make this look a little better. A is isomorphic to Z mod P to the beta 1Z cross Z mod P to the beta 2Z cross 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 Z mod P to the beta TZ, where beta 1 is greater than or equal to beta 2, which is greater than or equal to, keep going down the line, up to beta T, which is greater than or equal to 1. And the sum, beta 1 plus beta 2 plus beta T, is equal to alpha. So again, checking orders, left-hand side, order P to the alpha, right-hand side, also order P to the alpha. And we've arranged these cyclic factors so that the biggest ones, the biggest P to the beta i's come first. P to the beta 2 divides P to the beta 1. These look like invariant factors, but now each one of these cyclic groups has prime power order. Okay, so we had this whole discussion where we said you start with the invariant factor decomposition of a group G, and then you get a partition for each prime P dividing the order of the group. What is this beta 1, beta 2 up through beta T given here? This is exactly that partition that I was describing. You know that G has an invariant factor decomposition. So how are we getting this group of order P to the alpha written as a direct product in this way? We're just taking how many times does P divide the first invariant factor? How many times does P divide the second invariant factor? And so on. So I'm just explaining how what we said about invariant factor decomposition leads to this decomposition here. So there's also a uniqueness part of this theorem that I'm going to pause and erase and state. But what I want to emphasize is that starting from this statement about the invariant factor decomposition, we see why we get this primary decomposition. So you can go from invariant factors to these product of cyclic groups in the primary decomposition theorem. So I'm going to pause and erase. I'll give you the uniqueness part, and then we'll talk about some terminology, and that'll be the end of this lecture. On to the uniqueness part of the primary decomposition theorem. This says that the decomposition given by parts 1 and 2 is unique. That means if G is isomorphic to this A1 cross A2 cross 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 AK, and if it's also isomorphic to B1 cross B2 cross 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 BM, well, this M first has to be equal to K just to make the orders of the right-hand side and the left-hand side match up. If you want the order of BI to be PI to the alpha I, right? So now the right-hand side really is the same as the order of G. And it has to be true that each BI has to be isomorphic to AI. I mean, they have the same orders, but more than that, they have to be isomorphic and they have to have the same invariant factors. Okay, so let me say something about notation. These integers, P to the beta J, that show up in this part 2, when you're writing each one of these prime power order subgroups in this direct product, as a product of cyclic groups, these P to the beta J's, these are called the elementary divisors of G. And they're different than invariant factors. For each prime P dividing the order of G, you get a set of elementary divisors. So there's not just one set, there's one set for each prime dividing the order of G. And this decomposition that you're given here, first G is a product of prime power order subgroups, and then each prime power order subgroup written as a product of cyclic prime power order subgroups. That's the elementary divisor decomposition of G. And let me say something about where we are. So this first part is just saying G is a direct product of some group of order P1 to the alpha 1, some group of order P2 to the alpha 2, up to some group of order PK to the alpha K. But a subgroup of G of order P1 to the alpha 1 is a Sylow P subgroup of G. We've already seen that if G is a finite group of order n, which can be written as P1 to the alpha 1 up through Pk to the alpha k, and the number of Sylow P to the I subgroups is 1 for each prime Pi dividing n, so for each I, then G is isomorphic to a direct product of its Sylow subgroups. So it's a direct product of P1 cross 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 Pt, where, sorry, this should be Pk, right? It's the number of primes dividing n, where Pi is the unique Sylow Pi subgroup of G. So in fact, we saw more. We saw an if and only if statement that G was isomorphic to a direct product of its Sylow P subgroups if and only if every one of those Sylow P subgroups was unique, or equivalently that they're all normal. I didn't give the reference at the time, but this is a version of Theorem 3 in section 6.1 of Dummett and Foote, which shows the equivalence of a bunch of different statements. This is the equivalence of 2 of those statements. Some of the other ones won't make sense yet, but if you want to go ahead, you can read ahead and see where that theorem is written down in a slightly different presentation than given in Conrad's notes. Okay, why did I bring this up? Well, in an abelian group, every subgroup is normal. So that means that there's a unique Sylow Pi subgroup for each prime Pi dividing the order of n. So we already know that G is isomorphic to a direct product of its Sylow P subgroups. So where's the meat in this primary decomposition theorem is that it's not clear at all that each one of these Sylow pi subgroups decomposes as a direct product of groups that look like Z mod P beta 1Z cross Z mod P beta 2Z, and so on. So the interesting thing going on here is statement 2, that you can decompose each one of these prime power order subgroups in a nice way as a direct product of cyclic prime power order subgroups. So if you believe the fundamental theorem of finitely generated abelian groups, then you can go from the invariant factor decomposition to this decomposition. But the fundamental theorem of finite abelian groups, finitely generated abelian groups, is hard to prove. So we will see a full proof of that theorem, but not until 206b, when we talk about the classification of modules over a principal ideal domain. So that shouldn't make sense yet. We'll get there. That's chapter 12, section 1, I think is where you might want to go and look that up. But if you restrict from finitely generated abelian groups to finite abelian groups, we can prove this statement with the tools that we already have. So what we're going to do is, in the next lecture, we'll first start with some explicit examples of going back and forth between this elementary divisor decomposition and the invariant factor decomposition. Then we'll talk about recognizing direct products. Like if you're given a group, how can you see that it is isomorphic to a direct product of two of its subgroups? And that recognition theorem for direct products will be the big tool that we have to use to prove part 2 of the primary decomposition theorem, that you take one of these prime power order subgroups of G and that you can decompose it as this direct product of cyclic prime power order subgroups. So that's the plan. In the next lecture, we'll start with some examples. We'll talk about recognition theorem for direct products, which is section 5.4 in Dumb and Foote. And then in the next lecture after that, we will prove parts 1 and 2 of the primary decomposition theorem. We won't do uniqueness in lecture, but you'll have the tools to prove that if you want to go ahead and do a little bit of extra work.